Hi, in this series of videos, I'm going to try and show how to wire up an all-in-one DC from Centroid. It's an effort to try and simplify the major components of the all-in-one DC and how each subsection is wired up. Now, this is my interpretation of the Centroid schematics and what's provided by Centroid. You have to do your due diligence and study the drawings and figure out what's best for your application. I'm not responsible for what you do on your end. It's impossible for me to predict what you have and what you do. This is just an overview, an outline, if you will, of the things that you need to do to wire up an all-in-one DC. What I have here on the board is I have an all-in-one DC drawn up, and I've got the inputs 1, 2, 3, 4, 5, 6, 7, and 8, and then 9, 10, 11, 12, 13, 14, 15, and 16 shown, and then the outputs across the top. Each of these outputs is fused, and outputs 8 and 9 are single pole double throw relays. I've shown contacts here, but the all-in-one DC plate has, it's probably a little bit clearer, and or the schematic of the all-in-one DC. One important thing to note, make sure you download the latest schematics from Centroid. They've actually broken things down so that it's not like they're full-on schematic. They try and do the same thing. They try and help you wire the subsystems. And that's what we're going to do today. We're going to wire subsystems. We'll probably do one subsystem, then wipe it off the board, then do another subsystem, wipe it off the board, so the board doesn't get too busy and it's clear, rather than a whole, do one subsystem, then add another one, then add another one, and so forth. So that's the approach that I'm going to take, and hopefully it helps clarify things for you. I'm an electrician by trade. I have basic electronic skills. I served about 30 years in the public sector in traffic signals. In the last 10 or so years, I was the supervisor for the city of Mesa here in Arizona. So I have the background to do this sort of thing. And even so, it can get, kind of intimidating. It's still intimidating for me to look at the print, take the time to follow things through and not guess things, because the last thing you want to do is burn up your all-in-one DC, and you're on the hook for that. If you do something and you make a mistake, and you're contacting the folks at Centroid, make sure you're very clear and you're very specific as to what you were doing or what you think happened when whatever happened. It's just be honest about things. Centroid does offer technical support. They can actually remote into your control, provided your computer, your CNC PC has Wi-Fi or a connection to the internet, which is extremely helpful. They can help configure the software if needed after you've gotten everything wired up. You might want to watch my other video on my CNC and email conversion, where I wire up an all-in-one DC, and I go through the Centroid installation manual for the all-in-one DC step by step, and that's the way you should do it. You should definitely take the time to read through that manual before you do anything, and then as you go along, take it in sections, one step at a time. It's really important. If you are not familiar with electricity or electronics, then I suggest you find a friend or somebody who is, that can help you through the process. You don't want to hurt yourself, and you don't want to damage anything. And you certainly don't want to go into a project, start one, and end up with a bunch of expensive parts that aren't doing anything. So, the outcome is hopefully you have a running CNC machine at the end. So, again, reach out to somebody, a friend, or somebody that can help you if you need it. All right, with that, let's kind of go over the major components of the all-in-one DC control cabinet. Up here at the top, this is a rotary switch. Here's a picture of one. It's basically a safety switch, just basically turns on and off power. And in this, what I'm showing here is, I'm assuming single phase rather than three-phase, most certainly you could have a drum switch with 3 terminals. You can have a drum switch with 3 terminals and 2 auxiliary terminals, which is what the all-in-one DC schematic shows. They assume 3-phase. 3-phase is basically for motors like your spindle motor, coolant pump, that sort of thing. But you know, I'm going to guesstimate that most people doing this conversion are going to be using single phase in their home shops. 3-phase is just basically wiring up and taking into consideration your spindle motor, variable frequency drive, or reversing contactors. If you're just going to use, say you have a gearhead machine and you switch gears that way, you need to be able to switch it from forward to reverse direction. So anyway, we're going to concentrate on single phase. So here's a drum switch, disconnect switch. L1, L2, L3 are on the top. T1, T2, T3 on the bottom. L1 is line 1. So that's the way you should always wire something. Power coming in should always go to the L terminals. Power going out should always go from the T terminals. And then you have a landing block for the AC minus. Now, the all-in-one DC uses 120 volts, has its own circuit to control the control itself, the CNC PC, and power to the servo motors. So it's a 120 volt circuit. So between the 120 volt circuit and the AC minus, that constitutes the circuit. It's a dedicated circuit. Over here is a 240 volts. That's going to feed a variable frequency drive, or it's going to feed your contactors in your machine if you so use them. So that's what we got here. Over here we have a step-down transformer. Most applications, your servos have a max terminal voltage. If it's 90 volts or if it's 110 volts or something like that, DC, then you have to step down the 120 volts. You have to use a step-down transformer, so you're basically going to come out off of power, your line side, with your AC in, and then you're going to have AC out. This does not create DC voltage. All it does is step down your AC voltage. I have a couple examples here. There's a multiplier, 1.414. So your AC input times 1.414 will give you, I say DC out. That's what you're going to get once it's rectified. Rectification means it comes out of the transformer, it goes through a bridge rectifier and a filtering capacitor, and then once that's done, what you have at the positive and negative terminals is this DC output. I have a couple examples. If you put 24 volts, if you have a transformer that steps down 110 volts to 24 volts, and then you rectify that times 1.414, you're going to get about 34 volts DC out. If you have 48 volt transformer, so 110 comes in and 48 volts comes out, once you rectify that, you're going to have 67.8 volts DC out. So that would be good for you know, a 70 volt max terminal voltage DC motor. You know, it might even be fine for a DC motor that's 90 volts max terminal voltage. You're at 70. You know, you won't have as much top-end RPM, but it still might be fine for your application. And sometimes it's kind of difficult to find a step-down voltage to get right to where you want to be exactly. So you want to be just, you know, anything below the max terminal voltage of your servo motors. So that's the step-down transformer. In some cases, in my case, in my mill conversion, I rectify directly the 110 volts coming in, and it gives me about, I think it's 170 volts out. So when I take 120 volts in, I rectify that through the bridge, the filter capacitor. I rectify that and I get about 170 volts out. My max terminal voltage on my motors is 180 volts DC. So you may have that possibility, in which case you don't need the step-down transformer. So it's just a point of interest. The next item here is an Estop contactor. It's basically, its coil is tied to the all-in-one DC's Estop contact output, and it's that series through the Estop button. This is our e-stop button at the top. So that if you have an e-stop and you hit that, it opens this contactor. The contacts are normally open, and then it energizes and closes everything. In normal operation, it'll energize and close all these terminals. In this case, there's 5 terminals, L1, L2, L3, L4, a 13 and a 14. These are auxiliary. You may not need all those. You know, you only may need 3, or you may need 4. It's easy to find a 4-pole or a 3-pole relay. Pole meaning these are poles. It's easy to find an L1, L2, 3 relay with an auxiliary contacts, fairly easy. You can buy the 5-pole relay from Centroid if you need it. The all-in-one DC schematic that I happen to be referring to uses a 5-pole relay, but you may not need it. So, you know, we'll talk about things that run through it. One of the things, one pair is dedicated to the DC out. Once it's rectified from the capacitor, it comes over, goes through 2 of these. They're breaking both the positive and negative circuits, and then it comes out here and it goes to the all-in-one DC H2 voltage minus and voltage plus on the board. The other thing, another contactor is if you have flood coolant, a flood coolant will come through here. If it's say a 3, if you need a relay to turn it on and off, you can run that relay through this, so that if you hit the e-stop or if the all-in-one DC sees a fault and it opens this, it turns off the flood coolant. You know, that's just an example of things that run through here. The heart of the wiring is this TB1 terminal block. It's a 15-position terminal block. On one side is A, one side is B. Each terminal from top to bottom is numbered 1 through 15. The all-in-one DC schematic shows the first 3 are tied together, so they have a tie bar between the first 3. That's what these are, tie bars. Or if you can't find tie bars, if you're, you know, a lot of terminal blocks, you can purchase these little shorting shunts that basically loop the screws together, and then you land your forks or whatever on top of it. If you're using DIN rail, they usually have tie bars that go right in the middle, and you screw them together so you can tie them together. So the first 3 are tied together, and that's AC plus. The second 4 are tied together, that happens to be AC minus. The third 3 are this next batch of 3 is tied together, and that's chassis ground. And then 11 is 24 volts plus, and then minus 24 volts here on this last batch here. So that's the TB1, the terminal block. We've got our capacitor here, and our bridge. Bridges, you know, they're kind of a square, and they're typically marked on the side. I'll show a picture of an example of a bridge rectifier, but it's important that you wire them correctly. So in this case, this is the little sine wave, and this is a little sine wave. So once you're coming off of AC, say your transformer or whatever, AC will go to the little sine wave here, and AC will go to the little sine wave here. One thing of note, you might and probably need a current inrush device, and I'll show you a picture of that. And basically what it does is, you know, depending on the size of the cap, when you throw power to it, it pulls so much current and voltage it may trip your circuit breaker. And that inrush device goes right here. Kind of looks like a small lollipop. And then your AC will go right here. So you come in here with AC, and then the other end of this inrush limiter goes to this AC terminal, and then your other AC terminal is here, and then you've got your DC negative coming out, going up to the capacitor, and your DC positive going up to your capacitor, and then you come off of these terminals. Then you'll go through the Estop contactor and then over to H2 VM minus and VM plus to supply voltage to the all-in-one DC, which in turn supplies the voltage to the servo motors. So you may need this current inrush limiting device. You can certainly buy this entire unit from Centroid. They have it all made up. It's a really nice package. Or you can piece it together. If you can find, the capacitor is usually the expensive part because it's large. It can be 6,000 microfarad, it could be 9,000 microfarad. That capacitor has to be rated above the voltage that it's going to be filtering. So if you're going to filter, you know, 120 volts and then it gets rectified, then it's going to be rectified up to 180 volts. That capacitor needs to be rated higher than that 180 volts. So, you know, a 220, 250 volt capacitor to give yourself some leeway, otherwise that capacitor can blow up. So, you know, make sure, you know, if you want to be on the safe side, just buy the thing from Centroid. It's already done, already built. It's very clean, nice. All this is built right on top of the capacitor. You just go AC in, DC out. It's a real clean setup. So that's the this is the bridge. This thing's going to convert the AC to DC for us. Over here we have a power supply. This power supply feeds the positive 5 volts, negative 12 volts, positive 12 volts in common to the input of the all-in-one DC. That's what they call logic power, and logic power is H1 on the all-in-one DC. Now one terminal that isn't, one secondary output that's not used is 24 volts DC. That you can use that, and that's what we're going to talk about here in a second for limit switches, low voltage relays, and that sort of thing. You can use that 24 volts. The one thing, I think it's 1 amp, 24 volts out, so make sure that your coils and whatever you're driving isn't going to exceed that. Because if it does, it can pull down this power supply and might affect the quality of the voltage going into the all-in-one DC and create all kinds of trouble. And I went through that and am going through it with my my mill conversion. Long story short, my DC, 24 volts DC was, you know, almost being pulled to a short, and it had an effect of messing with the power quality of the logic into the all-in-one DC, and the all-in-one DC was throwing up some goofy error codes, communications errors and things like that. So, you know, your power's got to be really clean and good. Another thing that we need to talk about before we get a little bit further along is the voltage on these inputs. These inputs, you have banks of inputs. I say banks of 4. You have 4, 8, 12, 16 inputs in the all-in-one DC. Each bank of 4, those inputs, you have to set a resistor in the all-in-one DC, and I'll show a picture of that. You need to set a resistor in there depending on the voltage you're using. My suggestion to you is try and use 24 volts DC and set, these are the little green lines represent the resistor pack, single inline package. The value of that resistor is dependent on what voltage you are going to be inputting into the all-in-one DC. You can have, your choices are 5 volts, 12 volts, and 24 volts DC. So depending on which one of those you use, you can change these. Now you can do it in banks of 4. In other words, say you want to use 24 volts for your limit switches. That's what we have here, limit switches. You want to use 24 volts, and say for Estop, spindle fault, low lube, whatever, you want to use 12 volts. You can change these SIP resistors so that these banks are assigned to have 24 volts, and this one might be 12 volts, and this one might be 5 volts. So if you have proximity sensors or you have optical sensors, you know, that output a certain voltage, then you may have to change that. Again, I recommend keep it simple, make them all the same if you can do it that way, especially if it's a fresh build. In other words, you're adding, you're converting an existing machine to an all-in-one DC. Just go 24 volts if you can and go with it. Now, you know, if you have a tool changer, you have unique things, and you're forced to use a sensor, you can't replace them, you got to do what you got to do. But it's just an FYI if you can't keep them all the same. In my example, we're going to use 24 volts DC because that's what's available to us with this power supply. I don't recommend that you tap off of any of the logic DC circuits that feed the all-in-one DC. Leave that alone. Leave it alone. And if you need other voltages, then get yourself a different power supply and use that. Use that power supply for all that other stuff. Just make sure your power supplies, the commons are tied together, so that you don't have any issues because of that. But so anyway, so that covers our power supply. Of course, it's the all-in-one DC. You know, I did the best I can to lay this thing out. These are the output relays. All these outputs are fused. They come from the factory with 2 amp fuses, I believe, with the exception of the last 2. I think one of them, I think 9 has a 10 amp fuse. So that said, yes, there's something there, there's a fuse there, but depending on what you're driving, you probably want to change that fuse to be sized appropriately, you know. So that's just an FYI. I mean, let's go over these. The all-in-one DC comes, let me back up a little bit. So the software that controls the all-in-one DC, whatever revision it happens to be. Right now it's CNC 11. I think it's going to be CNC 12 before too long. But when you buy the all-in-one DC, it has a programmable logic controller in it, which basically says you can assign these outputs and inputs to whatever you need them to be. I haven't done it, but I don't think it's an easy task to do. It's probably something that you might have to, you can certainly try and do it. They do have a manual on their PLC. And you know, maybe I'll take a stab at doing it if I need to do it, and we'll cover it in a future video. But when you get this board, the all-in-one DC, it comes pre-programmed. The inputs and outputs come pre-programmed, which works pretty much for an email, works pretty much for you can use it for a lathe, a simple lathe without a tool changer, maybe a router, maybe a plasma cutter or something like that. You can use what's there already. And let me go over what it has. So the first output is Estop. The second one is a lube pump. So if you have an automatic lubrication pump, you can tie it to this. The all-in-one DC can regulate that lube pump. In other words, if the lube pump already has a timer in it, well, you can certainly use that. But if it doesn't have a timer circuit and it just, you know, as long as it got power, it just feeds, then the Centroid All, the software can regulate that lube pump, which is kind of cool. And that's what I'm doing on my Nemo. The second one, or the third one, is flood coolant. Fourth one is mist. It's just a contact closure. So sometimes if you have a flood coolant pump whose current rating, if it's single phase, even if it's single phase 120 volt or single phase 240, you can use this contact to make and break and turn the flood coolant pump on and off. As long as it does not exceed the contact rating of the all-in-one DC, and you may have to change the fuse on it, you can do that. Mist, if you have a mist coolant system and it's pneumatic and you need to turn on and off a pneumatic solenoid, 24 volt solenoid would be perfect because you get 24 volts here. You'd run 24 volts through this contact and then out to the solenoid and then back to common. So you could turn that solenoid on and off, or you could turn, if it's an AC type, you know, you could certainly do that. I think most everything is pneumatic, so you're going to turn a pneumatic solenoid on and off. I'd recommend using 24 volt DC for the solenoid, turn it on and off. The next one, number 5, is inverter reset. So if you have a VFD and it needs to be reset because it faulted, the all-in-one DC is programmed to be able to do that. The next one is work light. You power up your machine, the work light could be turned on and off automatically. You don't have to flip a switch. Number 7 is spindle enable. So to the VFD, you're going to enable the VFD. Or you could use spindle enable for, you know, turning on a contactor or whatever to the spindle system. The next one, 8, These are the single pole double throw contact relays. This is spindle direction. So in normal, it's in forward. When that contact flips, when it's called to go into reverse, when you do an M4 in your control, it'll flip this contact over and it'll send a signal going reverse. So if you got a VFD, you use both, forward, reverse to the VFD. So in one direction, it's obviously going to command the VFD forward. In the other direction, it's going to command the VFD in reverse. And number 9 is an auxiliary contact. It's not assigned, so it can be used for whatever you need it to be used for. Now let's go down the inputs starting from the bottom up, because they start with input 1 and they go to the top. The first 6 are preset for limit switch inputs, which is typical on an email, or you'll use X and Z for a lathe if you're using a lathe. So the first one is input 1 is X minus, input 2 is X positive, input 3 is Y negative, input 4 is Y positive, input 5 is Z negative, and input 6 is Z positive, limit switches. So you got limit switches on each end of the travel. If you don't have limit switches on one end, on the opposite end of the travel, say you home to X minus, Y minus, and Z positive on a mill, you don't necessarily have to have a limit switch on the other end. You can set up the software limits in the Centroid software, which will spare you from having to put that limit switch there. The caveat there is you got to make sure you program the software limits correctly in the software. So moving up to the next one is low lube. So if you have that automatic lube pump and it has a float switch inside of it, when the lube drops below a certain limit, that switch will open or close. It will send an alarm to the all-in-one DC, and that's a critical fault, and it'll stop until you put more lube in it. So that's what the low lube is. Spindle fault. So if your VFD faults, it's got an output that you usually program on your variable frequency drive. It closes a contact if there's a fault, and then this is where it would go. Estop input 11, that's your button. So there are 2 sets of contacts on the Estop, both normally closed. One of them is going to do nothing but go into this one from here. It's going to go here, and then the other one is going to go down to the negative. So it's just one circuit. So that's a logic signal that goes into the all-in-one DC. So if that button gets pressed, the circuit opens, the all-in-one DC goes into a fault, so the E-stop button's pressed. Side note here, to clear faults in the all-in-one DC software, you cycle the E-stop. The others are not assigned. You can assign them for whatever else you need. They're there if you need them. If you can't program the PLC, you can certainly get a hold of the guys at Centroid and talk to them about your needs and programming your inputs and your outputs. So I think that pretty much gives an overview of the major components here. Like I said, I'm going to try. It would get too busy if we try and just draw lines all over this thing, so we're not going to do that. We're going to take one component, one subsystem, let's call them subsystems at a time, and wire them up. We already talked about the resistors. You need to know that. The other thing is using wire strippers. There's 2 sets here. They're actually do 2 ranges of sizes. This is a Klein. They're both Kleins, but this one does wires from 16 to 26 gauge. Really nice, because a lot of the control wire, I use this 95% of the time, because the control wire is typically small and this strips it correctly. This one is typical electrician's strippers. It goes from 10 to 18 gauge. So you'd be fighting trying to strip 22 gauge with these. And likewise, if you're trying to strip 14 gauge, there is no 14 gauge. If you do 16 gauge, you're liable to nick the conductor inside the insulation. You don't want to do that. So it's really important that you strip the wires correctly. The other thing let's talk about is small wires and landing them underneath a set screw, like these control wires here. You have two options. You strip the end of the wire and then you can tin that end of that wire, solder up. It gives it some substance or something to bite onto, so when you crank down on it, it does grab it, but it doesn't tear up the individual strands of the fine wire of that gauge. So if that's one option. What you don't really want to do is just strip wire, stick it in there and crank on it with a screwdriver, because you can break those strands of wire. So you don't want to do that. The other option is using what's called a ferrule. Basically you strip the wire, you slip this over it, and then you crimp it. Let me grab my crimpers and I'll show you what that looks like. You can get them off of eBay really reasonably. You can get ferrules. You can get them on Amazon too, ferrules and the ferrule crimpers. They're really cool and they're time savers. What I did find is, they add more bulk to the wire. In other words, if you've got to try and get two wires onto one terminal, you might have trouble trying to get both ferrules under one terminal block or one terminal itself. Sometimes I've gotten away with slipping both wires into one little bit larger ferrule. As long as they go in there and then they crimp down on it, it seems to work well. It's just something to keep in mind. Let me get my ferrule and a crimper, and I'll just show you what that looks like. Okay, here's the crimper, and it's a ratcheting crimper. This happens to be a 6-sided die, and what it does is it comes down and it'll crimp the barrel of the ferrule. So you see the insulator, this is a large one, but the wire goes in here, goes into the barrel, and then you stick that barrel into the crimper, and then you crank, you cycle it, and when you pull it out, it's crimped the barrel around your conductor. I kind of like these. They're really inexpensive, they're time savers. You don't have to deal with a soldering iron, you don't have to deal with solder and soldering the wires and so forth. But like I said, it can add bulk. If you just got one wire that's got to go in somewhere, then that's fine. So I guess what I'm saying is these have a place, and 90% of the time they work great. Other times they're a little bit too bulky and you might want to go the tin the wire route, or you might use a fork terminal, standard fork terminal and crimpers. Same thing with insulated terminals, the typical fork type. You slip them over, crimp it, and then you slip it under a screw. Make sure you use the right tool to crimp those. What I'm getting at here is you want to make sure that your wires are terminated properly and you leave no whiskers. In other words, you get all the conductors, the strands in whatever you're crimping, or they get all soldered, and then so that you don't have a whisker, because the last thing you want is to stick that wire in and then that whisker's touching something else. It's especially critical when you're doing the encoder wiring in your servos. You don't want little whiskers anywhere. Even in the all-in-one DC, you don't want whiskers. Just get in the habit of terminating your wires properly. Okay, let's talk about screwdrivers. Recently, Klein Tools came out with this screwdriver, and I find it super wonderful. The reason why I like it is it's designed for terminal blocks, small terminal blocks. And it actually you can flip it. So there's a very small straight blade here and a little bit larger straight blade there, and you can just rotate it, depending what you need. This has been my favorite. And it's got a pad on here so the screwdriver swivels. Also, these can be flipped. So you have a small Phillips screwdriver. I haven't found that as handy yet, the small Phillips, but I really like this tool, this Klein tool screwdriver. It can be found on Amazon. I think I spent 11 bucks for it. It's probably the best. I liked it so much I got another one. Otherwise, Craftsman, here's an 1/8 inch blade screwdriver. I find sometimes that the flare here gets in the way when you're trying to tighten something, but it just makes things much more enjoyable when you have the right tool, and since you're trying to save a buck by doing a conversion yourself, and spend a little bit of money on the tools. All right, so that wraps up this first video on an overview of what we're doing. Talk about the tool stripping. We talked about the resistors that need to go on the all-in-one DC on its inputs. Now we'll get started on wiring up a subsystem.